Okay, let's get going on the Chapter 6 review, which is on the topic of discrete and continuous random variables. In fact, the first part of the notes is to understand the difference between a discrete and a continuous random variable. And so the difference between the two has to do with the possible outcomes for the variable. So the difference is that for a discrete random variable has a countable number of outcomes, whereas a continuous variable has infinite possible outcomes. So let's say continuous has infinite outcomes. So let's talk about a couple of examples for each one of those. For a discrete random variable, that would be something like the number of correct answers on a test. Okay, you could have 5 correct answers or 6 or 7, but you couldn't have decimals for number of correct answers. Or something like number of shirts. Okay, that has a countable number of outcomes and is therefore discrete. For continuous, we need to think about some variable that has infinite possible outcomes, and the one that comes to mind is times in a race. 2 minutes 24 seconds. 2 minutes 25 seconds. Well, it could be 2 minutes 24.32 seconds. So there's actually an infinite number of possibilities when we talk about times in a race. Or weights of something. 4.23 pounds is certainly acceptable. So that would be considered a continuous random variable. Okay, so if we talk about first the discrete random variables, the first thing I have you do here in the review is to draw a probability distribution. Okay, a probability distribution has to have a list of the possible outcomes for x, along with the probability of each one of those occurring. So we generally give it in a table like this, where we would list out the possible values for x. x1, x2, x3, x4, all the way up to xn, because there has to be a countable number of outcomes here. And then for the probabilities, well, they could have different probabilities for each. I'll just say p1, p2, p3, p4, all the way up to p sub n. So if you are given a probability distribution like this, you need to be able to calculate the expected value, which is the same thing as the mean, and they will use both terms. They may ask for an expected value, they may ask for a mean. And we know how to calculate means as simply the average of a bunch of numbers. Well, in this case, I cannot simply add up all of the x values and then divide by the number of numbers, because they are not all equally weighted. So we need to take each individual x value and multiply by its probability. So x1 times p1 plus x2 times p2 plus x3 times p3 plus ... Now there is a nice short way of writing that using sigma notation. It is simply the sum of x sub I times p sub I. In fact, that's the formula that you'll see on the formula sheet for the AP exam. Okay, and that will give you the mean or the expected value for a probability distribution. Now for the variance, the way that you will calculate that is you will take each individual x value. So I would start with the first x value, x1, and you want to figure out how far it is away from the mean. So I would subtract mu sub x, which is the mean. Now sometimes that's positive and sometimes it's negative. So we take that value and we square it. And then we need to weight that value according to the probability. So in this case, p1 would be the probability of x1. Plus, do the same thing for x2. x2, subtract the mean, square it, multiply by its respective probability. Plus, ... Now the nice short way of writing that using sigma notation, it is the sum of each individual x value, x sub I, minus the mean, mu sub x, quantity squared, multiplied by the respective probability, p sub I. So there is your formula for the variance. Now, if I asked you for standard deviation, you would, of course, calculate the variance and then simply take the square root of it at the end. Okay, now let's talk continuous. Well, for continuous, I can't give you a probability distribution like this with x's and p's because there are an infinite number of possible outcomes. So instead, what you will be given is what's called a density curve. And very often, your density curve might look like this, a normal distribution. So a normal distribution is really just a density curve for some continuous random variable. So if we talk about expected value here, the expected value, of course, is the same as the mean. And if you are given a density curve, it is the balance point. Well, we know for a normal curve, because it's symmetric, that the balance point would be right at the center of the distribution, or should be. So let's talk a few rules for means and for variance. And I have a scenario set up here. I say, suppose you have a list of numbers, and you know that the mean is mu, and you know that the standard deviation, we know the variance is sigma squared. So it says add 27 to each of the numbers in the list. Okay, we're going to add 27 to each of the numbers in the list. And we want to know what happens to the mean. Well, if you are adding 27 to every single value, that is going to add 27 to the mean. Now, let's think about what that would do to the variance. And really, you need to think about what variance is a measure of. And what variance measures is the spread of the distribution. Okay, how spread out are the values? So if you add 27 to every single value, what you're going to do is you're going to take that whole distribution and shift it 27 units to the right. Now, is that going to change the spread of the data? Of course not. So what happens to the variance? Nothing. It stays the same. Okay, now it says instead of adding 27 to each of the numbers in the list, what if you have multiplied each number by 11? Okay, we multiply each number by 11. First, we want to know what would happen to the mean. Well, if we take every number and we multiply by 11, that's what happens to the mean. It gets multiplied by 11. Now the variance, which we just said, is the spread of the data. If you multiply every value times 11, the values are going to get more spread out. Your lowest value and your highest value are going to be more spread out. And what you might want to say is that the variance gets multiplied by 11. But in fact, the variance gets multiplied by 11 squared, or 121 in this case. So if we were to write these rules up here, the first rule says the mean of a plus bx. So what they're saying there is that you're going to take your random variable x and multiply every value times b, and then add a to it. Well, we know that multiplying every value times b is, of course, going to multiply the mean times b. And then adding a to every single value, we just said, is going to add a to the mean. So b times the mean of x plus a. Now, if we think about what would happen to the variance of a plus bx, well, when we take all of our x values and multiply by b, we just decided that that would multiply the variance by b squared. So it would be b squared times the old variance. And then when we add a to every single value, that will do nothing to the variance. So that is the end of the formula right there. Now a couple more here. The mean of x plus y, this is exactly what you would expect. It is simply the mean of x plus the mean of y. And then for the variance of x plus y, well, it says here that it is the same as the variance of x minus y. And this is something that we should remember, that you just simply add the variances. Okay, notice so that we are not adding standard deviations here, we are adding variances. Also notice that even if you are looking at the difference between two random variables, you are still adding the variances there. You are not subtracting the variances. Okay, so let's take a look at this example here. I'm going to flip to the next page for this one. And all I'm asking you to do here is I've given you a probability distribution, and I want to calculate the mean and the variance. Well, we know the formula for mean. It's even on our formula sheet. The sum of x sub I times p sub I. So we are simply going to take each x value and multiply by its respective probability, and then add them all up. So essentially what we're doing here is a weighted average, okay, where each value is weighted by its probability. So if you type that all into your calculator, it should give you a value of 54.3. Okay, that would be the mean. Now if we want to calculate the variance, we know the formula from the formula sheet. It says take each x value, subtract the mean, square it, and then multiply by the respective probability. So we would take our first x value, 10. We would subtract our mean, 54.3. We would square it, and then we would multiply by its respective probability at 0.1. Plus, take the next x value, subtract the mean, square it, multiply by its probability. Plus, the next x value, subtract the mean, square it, times its probability. Plus, the next x value, subtract the mean, square it, multiply by its probability. And I will tell you, if you punch that in your calculator, you should get 1367.6. Now, a little shortcut here that you can remember from the calculator. If you put all of your x values in list 1, and you put all of your probabilities in list 2, you can then do a one variable stats, but tell the calculator list 1 is where the values are stored, list 2 is where the probabilities are. It will in fact give you the same answers that you see here. So I think it is important to be able to do this with the formula because this is shown up on the AP exam, but I really like the calculator way of at least checking your answers so that you know if you've done things correctly. Okay, on this last page we are going to discuss two things, binomial distributions and geometric distributions. Of the two, binomial distributions are certainly the most important and will definitely show up on the AP exam in both the multiple choice as well as the free response. So I'm going to focus a little bit more on the binomial here. And we'll start with the conditions. And there is a way to remember the four conditions, and that is BINS, B-I-N-S. So let's talk about what each means. Okay, B, of course, means binary, which really just means that every trial can be classified as a success or failure. And remember, success does not always mean something awesome happened. Okay, sometimes a success may be a broken light bulb or failing a test or something like that. You define what a success is and what a failure is. I, of course, is independent, and that really just means that each individual trial is independent of the others. N is for number. It is the fixed, that we have a fixed number of trials. And this is important. And typically we are going to use lowercase n to represent the fixed number of trials. And then S is that the probability of success is the same for each trial. Now this probability of success for each trial, we will usually use lowercase p to represent that. So in general, when you want to identify a binomial distribution, we use capital B, and the two parameters we put in parentheses are n, the fixed number of trials, and p, the probability of success for each trial. So let's talk a couple of formulas. If we want to find the probability of exactly k successes, I need you to underline exactly. Exactly k successes. Here's the formula. And you guys have actually seen this on your formula sheet already. You would do n choose k, and then the probability of success, p, raised to the number of successes. In this case, we're talking about k successes. And then the probability of failure, which is 1 minus p, raised to the number of failures, which would be n minus k. Now realize on the formula sheet for the AP exam, they do not write it n choose k. They write it with parentheses like this, n on the top, k on the bottom. Okay, so those are the same. Now on the calculator, you can do this formula by using binomial PDF. Okay, the probability distribution function, PDF. Now the way it works on the calculator, you always put in n comma p, and then you put in k, which is the number of successes that you're looking for. Okay? So that is the probability of exactly k successes. In the next part, it says if we want to find the probability of less than or equal to k successes. So now, I'm talking about the probability that x is less than or equal to k. Well, the calculator shortcut for that is binomial CDF, cumulative distribution function. Okay, remember what cumulative means, everything up to that value, which makes sense if we're talking about x is less than or equal to k. Now the arguments are exactly the same, n comma p comma k. Okay, a couple more formulas. Expected value, which we know by now is the same as the mean. And this formula is on your formula sheet for binomial distributions. This is simply n times p. Now for the standard deviation, it is the square root of np 1 minus p. Okay, so that takes care of the binomial setting. Let's talk a little bit and not much about the geometric setting. Typically this will show up in one multiple choice question, and that is all. You will not see a lot of this geometric distribution stuff. So I'm going to go through this very quickly. As far as your conditions for geometric, there are 4, and instead of bins, it is bits, B-I-T-S. And 3 of the 4 are exactly the same. Okay, number 1, binary. Number 2, independent. And number 4, probability of success is the same. Okay, those are exactly what they are for the binomial. The difference is the third one. And T says that we are looking for the number of trials until the first success. Number of trials until the first success. So that is the one that you want to put a star by because it is different. And because we are looking for the number of trials until the first success, there is no fixed number of trials. So in this case, there is no n. There is no fixed number of trials because we don't know how many trials it will take to get the first success. So let's talk a couple formulas. Okay, first of all, the probability of exactly k trials until the first success. Well, if it's exactly k trials till the first success, you need to think about how many failures we had previous to that. Well, if it's k trials till the first success, then there were k minus 1 failures first. So I'm going to take the probability of failure raised to the k minus 1, and then the probability of success raised to the first. Now on the calculator, we can do this with Geomet PDF. And then the arguments are p comma k. Now it says in the next thing, if we want to find the probability of less than or equal to k, less than or equal to k, that's when we're going to use the CDF. Geomet CDF p comma k. And then the expected value, I gave you this formula back in chapter 6, was 1 over p. And the formula for standard deviation, I did not give you because you will not need it. In fact, I'd like to put a big X through this part of the geometric because I think that it is very unlikely that you would need those formulas or to use those calculator functions. To me, this third condition being different is what's going to be important for you. Okay, so let's just take a look at these last example problems here. Okay, Mr. Wilcox makes 70% of his free throws. Okay, part A. How likely is it that he will make exactly 7 out of 10 free throws? Okay, first of all, let's check to make sure this is binary. Okay, success or failure, we have that. A made free throw is a success. Independent trials, we would assume that each shot is independent of the previous. Now, the fixed number of trials here is 10. That is our n value. And then the probability of success, 70%. So it is, in fact, binomial. And what we're looking for in this problem is the probability of getting exactly 7 successes. So let's try it using the formula first. Okay, you would do n, choose k. Well, that would be 10, choose 7. That's the number of different ways of making 7 free throws out of 10. times the probability of success, 0.7, raised to the number of successes. In this case, we have 7 successes. Probability of failure, well, how many failures would we have? If we made 7, that means that I missed 3. So you punch that into your calculator, and I'll tell you that comes out as 0.267. Now, we could, of course, have done this with the calculator function, and this one would be a binomial PDF, because it's exactly 7, and so we would do 10, comma 0.7, comma 7, and I will tell you that that comes out as exactly the same as if we had used the formula. Now, part B says, how likely is it that he will make 7 or more free throws? Okay, think about this. The probability that x is greater than or equal to 7, that is 7 or more. So if it's 7 or more, what I'm really looking for is the probability that x is 7, or 8, or 9, or 10. Now, I could find each one of those individually and then add them all up. But the easier way is to use binomial CDF and subtract the ones that I don't want. The ones that I don't want would be 6 and below. So I can do 1 minus binomial CDF for 10, comma, 0.7, comma 6, because then we would be getting rid of 6 and lower. And I'll tell you that comes out as 0.650 is the answer there. Okay, now the last one says, what is the expected number of makes? So when you see the words expected number, you should think mean. This is a binomial distribution, so we know n times p will give us the expected number. 10 times 0.7, which is 7. Okay, which seems to make sense. The expected number of makes out of 10 should be 7 if I'm a 70% free throw shooter. All right, hope you guys have a great Friday. I will see you on Monday.